Okay, so how do we calculate a cross product? There are two ways to do it. You have to be able to do both. One's kind of a long computational way, and the other is a quick way, and you really have to be able to do both. So here's the quick way, which is related to what we saw here. The magnitude of the cross product is given by the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between them. So if this is A, and that's B, and that's theta, AB sine theta, that's the magnitude of the cross product. Now, does that correspond to what we saw? When the two vectors were right angles to each other, sine theta was 1, and we got kind of a big purple arrow. When the two vectors were either on top of each other or anti-parallel, sine theta was 0, and we got 0. So that's the magnitude. The direction is given by a right-hand rule. And this is one that you have to use your right hand for. So everybody get your right hand out. Okay? And what you do is you hold your hand like this, and for this part, okay, let's not do it this way. You hold it your wrist has to be straight, okay? Your wrist can't flop. No floppy wrists. So you put your fingers in the direction of the first vector, and then you curl your fingers through the angle theta toward the second vector, and your thumb sticks out in the direction of the cross product. So in the way we've got A and B here, A cross B, the cross product would be into the board. So 3 dimensions. And it's all, the order matters, because let's do B cross A. Okay? If we do B, now notice that if we point our fingers in the direction of B, we're going to break our wrist if we try to curl our fingers up. So we actually have to rotate the wrist and then curl the fingers through theta, and now your thumb sticks out that way. And so B cross A is not the same as A cross B. The order matters. So it's always first vector, second vector. The angle between them is always smaller than 180 degrees. You always go the short way. Okay, so that's the right-hand rule, and you have to be able to do it that way. Once I had a student who came into a final exam with a big R written on the back of that hand and a big L written on the back of that hand, so that he would actually use the correct hand. Because if you're right-handed, it's really very tempting to keep the pen in your right hand and use your left. No. Left-handed people have a real advantage here. They can keep their pencil in their left hand and do the cross products with their right hand. But however, there's another way to evaluate it numerically, and it looks like this. So A cross B is the following vector. This is, got to get it right, okay, A sub y times B sub z minus A sub z times B sub y. That's the x component. And the y component is A sub z bx minus ax bz. And the z component is ax by minus ay bx. And how do you remember this order? Well, the usual mnemonic is to do this. You write this: x, y, z, x, y, z, with an arrow going to the right. And the way you interpret this is the following. If you want the x component, what are the next two things, y and z? So the x component starts out yz minus zy. Okay, now let's say we want the y component. What are the next two letters? Well, the next two letters are z and x. So the y component would be azbx minus axbz. And now if you want the z component, The next two letters are xy, so we have ax by minus ay bx. And a lot of times some of these terms are 0, which is really nice, but sometimes you just have to crank through the whole thing. And sometimes this will be the thing you want to do, but you can see that it's actually going to be pretty simple to do magnitude of A, magnitude of B, sine theta, and use your right hand to get the results. Okay, so let's try some. There are two vectors, 0, 0, 3 and 0, 4, 0. What is the direction of that cross product? And the choices are plus x minus x, plus y minus y, plus c minus c. And what I recommend doing actually is get out your right hand. Imagine those coordinate axes and just do it with your right hand. So let's see what we... Well, something about x is clearly correct because these two things are in the yz plane. So let's see, using our usual coordinate system with x to the left, y up, and z out of the board, the first vector would be this way, second vector would be up, and the thumb goes that way. And so I get negative x, which is what most of you got. If you got it backwards, it's actually important to be able to do this reliably. So think about it and try one more here. Okay, how about this one? We have 0, 4, 0 cross 0, 0, 3. Okay, everybody thinks that one's plus x, and let's see. The first vector goes up, the second vector goes out, so yeah, plus x. Okay, good, excellent. So what does this have to do with magnetic fields? Okay, so here is a charged particle. It seems to be red, so it must be positively charged. It's moving in the plus x direction. And we're going to look, do you want it in stereo? We can make it in stereo. Sure, we'll do it in stereo. So, moving along the x-axis, this is it would appear to be a positive charge. And we have to pick an observation location. So there's the r vector. That's going to be our observation location on the plus y-axis. Let's let it move. We'll watch what direction the magnetic field is in, and then we'll figure out what cross product we need to do to make this work. Okay, so here it goes. It's moving here. Not much for a while, and then we get a magnetic field. You like that? Plus z direction. Okay, so we can do it. Can we do it again? Sure, we'll do it again. Okay, so now think about, we have the v vector and we've got the r hat vector. I'm showing r, not, okay, but so think about what direction the magnetic field at the observation location is. What cross product do we use to get that direction? All right, what was the cross product? Is it V cross R? Or is it R cross V? Okay, we had V, and R hat was that way, so V cross R gave a magnetic field in the plus Z direction, which is what you saw, right? But R cross V would give a magnetic field in the minus Z direction, and that's not what you saw. So it looks like we got a V cross R. Okay, let's predict what it's going to be at another observation location. So an observation location on the Z axis. Okay, get out your right hand. We're going to do V cross R. V is still on the x-axis. And what point in the direction you expect the magnetic field to be going at that observation location? Where's everybody's thumb should be pointing. Uh-oh, we got thumbs up and thumbs down and thumbs to the right. So V is in the plus x direction. So I got V I got V in the plus x direction. R's there, so this is theta in the xz plane. And I can't rotate my fingers this way, so I better turn my wrist over so I can go V cross R. Thumb goes down, so I predict a magnetic field in the minus y direction. Let's see if it's right. All right. Okay, that looks right. Okay, this is the next observation location. What's the direction of the magnetic field on the minus y-axis going to be? Okay, what do we get? Negative z, let's see. Yep, negative z. Okay, well, for completeness, we'll do the observation location on the negative z-axis. Which way is the magnetic field going to go? Up. Okay, up. Let's see. Yeah. All right. Now, there is another case, however, that we need to think about, which is, what if it's an electron instead of a positive charge? So I'm going to change the sign of the charge to be negative. Now we've got an electron here. And we're going to look at first at that observation location on the... Okay, what do you think is going to happen? If it was a proton, what would the direction of the magnetic field be? It would be out. What do you think is going to happen if we flip the sign of the charge? Probably go in, won't it? Let's see. So let's do it. Yep. So it depends on V cross R, and it also depends on the sign of the charge. So here's the negative charge at a location on that axis. What's the direction of the magnetic field going to be? V cross R. Going to be up, positive Y, isn't it? So let's see. Yep. Okay, so that's the basic scheme. And we can put this together. Sorry, now you really have to come back to the world for a second here. Flat 2D world. Magnetic field, for some reason, is symbolized by B. And the formula for the magnetic field at some location R of a moving charged particle, we decided it had a V. It's actually typically written as V cross R hat. We decided the charge mattered, so there's a Q here, which could be a plus or a minus number. Not surprisingly, it falls off like 1 over R squared, so there's a magnitude of R squared. And then there's a constant which turns out to be called mu0 over 4 pi in SI units. This thing has the value of exactly 1 times 10 to the minus 7. And the units of magnetic field are Tesla. And so the units of that constant are going to be Tesla meters per Coulomb per second. And that gives us the magnetic field due to a moving charged particle at some location. You can get the direction. Now, the key part for getting the direction, everything matters for the magnitude, but for the direction, the first thing you do is you do V cross R hat, right hand. And the second thing you do exactly what you were just doing a minute ago. You say, what's the sign of the charge? If it's positive, it's in the direction of V cross R hat. If the charge is negative, I have to flip it. And that's basically all there is to it. So, real quick, one question. Positive charge moving in the plus y direction. Observation location here, somewhere in the XY plane. What's the direction of the magnetic field at the observation location? Well, not unanimous, and we need to be unanimous, so let's see what the story is. V is in the plus Y direction. Now, I got to curl my fingers. This would be R here, so I got to curl my fingers toward R, so I definitely have to rotate the wrist, curl the fingers toward R. Thumb points into the board, which is negative Z, so the majority wins.